This seminar is about the science and technology of thin films, which are extremely important in basic science and applied technology. This is a seminar that I presented back in 2007 in the physics department of King Fahd University of Petroleum and Minerals. The seminar consists of the following parts. First, I will talk about the importance of materials research, which is very much connected to thin films. And then I will talk about the deposition of thin films, then the growth mechanisms of thin films, after which we will look at the main properties of thin films and the characterization techniques used to determine these properties, and finally we will look at some applications of thin films. The presentation is of introductory level. It serves as a survey of the various areas of research related to thin films, which is a vast interdisciplinary field of research. Typical examples of the most common techniques, properties, and applications will be given. This is by no means exclusive or comprehensive. As I said before, it is like a survey of what we have in this field. Let's first talk about materials research and its importance. Material science and engineering is a discipline at the interface of science and engineering whose activities include the development of new materials with novel properties, improvement of properties of existing materials, studying the relationships between structure of materials at length scales ranging from 1 nanometer to 1 meter. It also includes the discovery of new methods of economically synthesizing, making, and processing materials and components with desired properties. It also includes development of new techniques for characterizing the structure and properties of materials. Material science and engineering is also important for predicting the performance of materials in engineering applications. The designations of early civilization eras reflect their materials development. The Stone Age, the Bronze Age, the Iron Age are all connected to specific materials. The technological progress in modern societies has been even more intimately associated with advances in material science and engineering. Material science is the enabling technology behind aluminum alloys, polymers, modern electronics, faster and fuel-efficient vehicles, novel energy storage, affordable housing, medical engineering, sensors, and nanotechnology. Materials science lies at the foundation of many areas, including forensics, biomedical applications, aerospace materials, mathematical modeling, craft and design, chemical engineering, quantum physics, and molecular genetics. The present and future challenges and opportunities in the field of material science and engineering are more exciting than those of the past, as engineers develop materials for more demanding applications. There is a continuous search for materials with higher stiffness and strength to weight ratios for aerospace applications. Electronic materials that allow faster data processing are being sought. Jet engine materials of lower weight, which allow safe operation at higher temperatures, are being developed. More corrosion-resistant materials for chemical industries are needed. High-temperature superconductors that may revolutionize the use of electrical power have been discovered recently and are being studied. To meet the technological demands for new materials, inter- and cross-disciplinary research is playing an increasing role in material science and engineering. The distinction between basic and applied research is disappearing. What is the connection between materials and industry? Why do we need to do materials research for industrial applications? Major technological breakthroughs came after advances in materials research. Materials research is at the core of modern technology. Various industries depend heavily on materials research, such as the petrochemical industry and the power industry. Examples of problems tackled by materials scientists include the study of corrosion, the development of ceramics, the development of fuel cells, and the development of sensors for various applications. So that was a brief introduction about materials research, materials science and engineering, and its importance in our daily life. Let's now start our discussion of thin films, and we will first talk about the deposition techniques that are used to synthesize, to make, to fabricate the thin films. We have first to talk about surface engineering, which is very related to thin films, because thin film synthesis or deposition can be categorized as a surface engineering process. Surface engineering refers to two things: covering the surface of a material, like a substrate, with an overlay, with a layer, and that means coating the substrate with a coating or thin film. It can also refer to modification, changing the properties of the surface of a material. So surface engineering can mean any one of these two. In the first process, in which we cover the surface with a layer, the substrate material is not detectable. In the second process, the substrate material is still present on the surface. Here are some surface modification techniques that are used to modify the surface of a material. They can be chemical processes like wet processing, exposing the surface to acidic or basic environments. They can be oxidation, where you let a stream of oxygen at high temperature to pass over the surface to oxidize it. They can be anodization of the surface with certain metal. All of these are chemical processes. We can also have physical processes like sputtering the surface, bombarding the surface with ions to change its properties. And we can also do ion implantation, where we bombard the surface with high energy ions that penetrate the material and change its properties. We can also have mechanical surface modification processes like planarization of the surface, polishing the surface, and grinding the surface. Finally, we can have thermal modification surfaces, in which we anneal or heat the material, of course its surface, to a certain temperature to change its properties. These are only examples of possible techniques, and usually you can have combination of these techniques to change the properties of a surface. Now let's talk about thin films. What is a thin film? The term thin film is applied to layers or coatings which range in thickness from a few atomic layers to several microns. So roughly we can say that the thickness of a thin film ranges from 10 nanometers all the way to 10 micrometers. Thin film deposition is a surface engineering technique. In some cases, surface modification can be used to modify the substrate prior to the deposition of the film. That means to prepare the substrate to accept the film on it, you have to do some of the preceding surface modification techniques to prepare the substrate before the deposition of the film. In other cases, a surface modification process can be used to change the properties of the coating after its deposition. So let's now look at the deposition techniques. How do we make the thin films? How do we synthesize or deposit them? Any thin film deposition process involves three main steps. First, the production of the appropriate atomic, molecular, or ionic species. You produce the material from which you make the film, and then you carry that material to the substrate, to the surface on which you want to grow the thin film. So the second process is the transport of these species to the substrate through a medium. The medium can be gaseous or liquid. The third step is the condensation on the substrate of these species, either directly or through a chemical or electrochemical reaction to form a solid deposit, which is what we call the thin film. Now, we will see many techniques, but they all share these three basic steps to synthesize the thin film. Here is an example of the techniques that are used to deposit thin films. If you read the literature, you will find hundreds of techniques to synthesize thin films. This is just a sample of the most famous techniques that are used to make the thin films. And we can broadly categorize them as atomistic techniques, techniques that stem from the atoms and molecules making up the material, and bulk techniques that are used to produce very thick films. The atomistic techniques can be categorized as physical techniques or chemical techniques. The physical techniques include evaporation, pulsed laser deposition, sputtering, and molecular beam epitaxy. The chemical techniques include chemical vapor deposition, atomic layer deposition, spray pyrolysis, and electrodeposition. Remember, as I said, that these are only examples of possible techniques. These techniques can be classified in many other ways. Okay, here we categorize them as atomistic or bulk. You can classify them as physical or chemical, vapor or liquid. So there are many ways to classify the materials. This is just one classification. The bulk coatings include techniques like dip coating, spin coating, sol gel, thick film, and screen printing. The way we will go through these processes is we'll classify them as you can see in here. So another way to classify the thin film synthesis techniques is to classify them as vapor techniques, techniques in which the thin film is made in a gaseous medium, or solution techniques in which the thin film is made in a liquid medium. And we will look at these 5 main techniques that are widely used to grow or deposit thin films. Let's start with the evaporation technique, which is a vapor technique. It goes in a gaseous medium. In evaporation, material from a thermal vaporization source reaches the substrate with little or no collisions with gas molecules in the space between the source and the substrate. And that is shown in here. You have the source, the orange block in there. This is the source of the material. It can be in the form of powder or pellet. So you apply heat to it to vaporize it. Make it in the form of atoms or molecules. These will travel from the source into the substrate. Once they impinge on the substrate, they form the desired thin film. The substrate can be on top of the source, it can make an angle with the source, and it can also rotate to make the film uniform. Vacuum deposition takes place in the gas pressure range of 10 to the minus 5 to 10 to the minus 9 torr. By that we mean we need to evacuate the space between the source and the substrate, and that will do two things. First, it will reduce the collisions between the molecules and the gaseous species, the air molecules, and second, it will result in very low contamination of the film, because you have no contamination. It's done under vacuum. The only thing that is there are the species that you are vaporizing from the source. Now, how do we do the evaporation? Evaporation can be done in three ways. Either by thermally heating the source. So here is the source. You apply heat to it electrically. You pass current in a conductor. That conductor will heat up, and from that heat you evaporate the source. So that's called thermal evaporation. You can also produce the heat by bombardment of an electron beam. So at the bottom here we have the electron beam. It is reflected through 270 degrees by a magnetic field. It has very high kinetic energy, and these high kinetic energy electrons, when they bombard with the source, they will produce a lot of heat that will cause vaporization of the source. The third technique is like the second one, but instead of using an electron beam, you use a laser. So you heat the source using a laser beam, a pulsed laser beam, that will produce a lot of heat to vaporize the material, and again this vapor will impinge on the substrate and synthesize the desired thin film. This third technique is called pulsed laser deposition or pulsed laser ablation. Vacuum deposition is used to form optical coatings, permeation barrier films, electrically conducting films, wear-resistant coatings, and corrosion protective coatings. These three techniques are broadly called PVD techniques, which stands for PVD, physical vapor deposition. The second vapor technique, a very important technique which is widely used, is the sputtering technique. Sputtering means the ejection of atoms from the surface of a material, which is called the target, by bombardment, by collision with energetic particles, and that is called sputtering. And that is illustrated in this drawing in here. Surface atoms are physically ejected by momentum transfer from the ions. Sputtered atoms travel until they strike a substrate. So here it is like evaporation, except that instead of heating the substrate like in evaporation, now we bombard it with ions. But the end result is the same. You have species coming out of the target, travel through some distance to impinge on the substrate and make the thin film. So sputtered atoms travel until they strike a substrate, where they deposit to form the desired layer. The bombarding particles are ions, creating by applying a high voltage to an inert gas, forming what we call a plasma. The target can be an element, an alloy, or mixture, or a compound. There are many types of sputtering. You can have direct current sputtering, which is applicable to conductors. You can have radio frequency sputtering, which applies both to conductors and insulators. You can also have reactive sputtering in case you carry out the sputtering process under a reactive atmosphere such as oxygen, hydrogen, or nitrogen. And we can also have ion beam sputtering, which is shown on the right here, where you have focused ion beam bombarding the target instead of having a plasma, which makes a random collision with the target. The third vapor technique is an extremely important technique, very widely used, and that is chemical vapor deposition, which is abbreviated as CVD. CVD is the formation of a film on a surface from a volatile, so it is in the gaseous state, a volatile precursor, as a consequence of one or more chemical reactions which change the state of the precursor. And that is illustrated in this diagram in here. The CVD technique is a very complicated technique, but it is worth the complication because of the advantages that we will talk about shortly. CVD can come in many variants. Here are some of the techniques, all of which fall under chemical vapor deposition, and all of which, each one of them is very widely used to grow certain type or certain class of materials. There are many variants. We have seen just some of them. Many variants of the CVD technique. One of them most commonly used is MOCVD, which stands for metal organic chemical vapor deposition. You can also have vapor phase epitaxy, atomic layer deposition, and even MBE, molecular beam epitaxy, can be broadly categorized as a CVD technique. What are the advantages of CVD? One advantage is the high growth rate achieved by this technique, which makes it economical. You can grow very thick films in a relatively shorter time compared to other techniques. It can deposit materials which are hard to evaporate. So when the evaporation by thermal or E-beam or lasers or sputtering fails, CVD offers an alternative that can work in that case. It is characterized by good reproducibility of the films grown. It can grow epitaxial films, which is an extremely important advantage of the CVD technique. But there are some disadvantages of this technique, such as the high temperatures. You have to grow films on substrates heated to very high temperatures compared to other techniques. It is a very complex process, and sometimes the gases used are toxic and corrosive. So these are the vapor techniques. We talked about three of them: the evaporation, the sputtering, and the chemical vapor deposition. And we have seen that under each one of them, you can have many processes. Let's now move into the solution techniques. Techniques that involve the presence of liquids. And here we will talk about two main techniques. The first one is the sol gel, and we will see that there are under the sol gel many sub-techniques. This process involves the transition of a material from a sol with fluid-like properties to a gel with solid-like properties. The sol is made of colloidal solid particles of submicron diameter, usually inorganic metal salts, and these are dispersed in a liquid metal organic precursor, which is called an alkoxide, that is dissolved in a solvent. Aggregation or polymerization leads to the development of an interconnected solid network with an interspersed continuous liquid phase, and that is the gel. So the gel is made. Now, how do we make the film? Thin films can be deposited by immersion of the substrate into the solution. In that case, naturally it is called dip coating, or by dispensing the solution onto a spinning substrate. In that case, it is called spin coating, or by spraying the solution onto the substrate, and in that case, it is called spray pyrolysis. So dip coating, spin coating, spray pyrolysis are variants of the sol gel technique. Following film deposition, thermal treatments cause a host of other processes like drying, solvent evaporation, densification, crystallization that shape the structure of the coating. Usually, sol gel is done at room temperature, so you have to heat the film after deposition to solidify the film and give it better crystallinity. The second solution technique is called the electrochemical technique, which is also called electrodeposition for brevity. Coatings can be made by anodic or cathodic synthesis. In the anodic method, a metal ion or complex is oxidized at the electrode surface. In cathodic synthesis, the cathodic process is used to generate a base at an electrode surface. Metal ions or complexes are then hydrolyzed by the electrogenerated base to form a cathodic deposit. What are the advantages of solution methods? With solution methods, you can prepare coatings with a wide variety of chemical compositions and microstructure. They are relatively cheap compared with the vapor techniques. Remember that solution techniques do not need any vacuum, so they are very cheap compared to the vapor techniques. And they are room temperature operation. You don't have to heat the substrates before film deposition. They can deposit on any geometry, flat or cylindrical or spherical. And they are commercial because they can produce coatings on large scale. So these are advantages of the solution methods. Finally, let's talk about nanostructured coatings. These include nanocrystalline coatings, nanowires, nanoparticles, and other nanostructures such as quantum wells. All of the conventional techniques that we talked about have been successfully applied to the growth of nanocoatings under controlled experimental conditions. There are two approaches to nanogrowth. The first one is called top-down approach, like the one used in lithography, and the second one is called bottom-up approach, where you grow the nanostructures from the bottom and let them grow vertically upward. Some techniques produce nanostructures directly. Other techniques produce nanostructures by post-deposition. That means you make the film, and then after the film, post-deposition, you let it go through one or more of these processes to produce the nanostructures. The post-deposition processes include annealing, heating the film under certain atmosphere at certain temperature for a certain duration of time, or by chemical etching, by ion beam bombardment, or by laser processing. All of these have been proven to produce nanostructured coatings out of typical or regular thin films. And that brings us to the end of the second part of the seminar, which is the deposition of thin films. Let's now move into the third part, in which we talk about the growth mechanisms of thin films. Formation of a thin film takes place through nucleation and growth processes. The general picture of the step-by-step growth processes emerging from the various experimental and theoretical studies can be presented by the following 6 steps. The thin film growth process can be very fast. Now we are playing it like a slow motion movie to see how the film grows on the substrate surface. The first step is called adsorption. The unit species, the atoms and molecules that are traveling from the source or the target, or that are formed by the chemical reactions in CVD, on impinging on the substrate, lose their velocity component normal to the substrate and are physically adsorbed on the substrate surface. So we move to the second step. Now we have the species coming to the substrate. Once they settle on the substrate, they start to cluster. The adsorbed species are not in thermal equilibrium with the substrate initially and move over the substrate surface. In this process, they interact among themselves, forming bigger clusters or nuclei. And that will lead to the third process, which is called nucleation. The clusters are thermodynamically unstable and may tend to dissolve in time. If the deposition parameters are such that a cluster collides with other adsorbed species before getting dissolved, it starts growing in size. After reaching a certain critical size, the cluster becomes thermodynamically stable and the nucleation barrier has been overcome, and that's the nucleation process. After the nucleation comes the island formation. So they go step by step. The critical nuclei grow in number and size until a saturation nucleation density is reached. This is influenced by the energy of the incident species, the rate of impingement, the activation energies of adsorption, desorption, thermal diffusion, and the temperature, topography, and the chemical and crystalline nature of the substrate. So it is a very dynamic, thermodynamic process. A nucleus can grow both parallel to the substrate by surface diffusion and perpendicular to the substrate by direct impingement of the incident species. However, the rate of lateral growth is much higher than the perpendicular growth. The grown nuclei are called islands. After the formation of islands, we have coalescence. What is coalescence? It's merging or melting or fusion of the islands. So, in this stage, the small islands start coalescing, merging together with each other in an attempt to reduce the substrate surface area. This tendency to form bigger islands is termed agglomeration and is enhanced by increasing the surface mobility of the adsorbed species, for example, by increasing the substrate temperature. The final step is continuous growth. Larger islands grow together, leaving channels and holes of uncovered substrate. The structure of the film at this stage changes from discontinuous island type to porous network type. Filling of the channels and holes forms a completely continuous film. Here is another way to look at the growth process, and these are called growth modes. We can have three growth modes. The initial nucleation and growth stages may be described as island type, layer type, or mixed type, mixed of island and layer types. The crystallographic orientations and the topographical details of different islands are randomly distributed. When they touch each other during growth, grain boundaries and various point and line defects are incorporated into the film due to mismatch of geometrical configurations and crystallographic orientations. If the grains are randomly oriented, the film is polycrystalline. However, if the grain size is small, the film is highly disordered and is amorphous. So, this is a brief description of the growth of thin films. Many studies, theoretical studies and modeling are dedicated to study the growth dynamics of thin films. With that, we will now move to the fourth part of the presentation, which is about the properties of thin films. There are, of course, tons of properties associated with thin films, but we will talk about just a few of them as examples of the rest. We will talk about the structural properties, porosity, and density. Then we will talk about mechanical properties, optical properties, and electrical properties. Let's start with the structural properties. The structure of thin films is strongly related to the deposition technique and the deposition conditions. The local arrangement of atoms in a film may be either regular, crystalline, or irregular, amorphous. Factors affecting crystallinity include the substrate nature. Is it amorphous substrate like glass, or is it crystalline substrate like a silicon wafer? Crystallinity is also affected by the substrate treatment. Is it polished, smooth, and etched? It is definitely affected by the substrate temperature. And if there is a lattice mismatch between the substrate and the film to be grown on that substrate. And finally, crystallinity is affected by the deposition technique itself and the deposition parameters during the growth and the post-deposition conditions after the growth. Epitaxy refers to single crystal film formation on top of a crystalline substrate. The conditions favoring epitaxial growth are high surface mobility, which is obtained with high substrate temperature, clean, smooth, and inert substrate surface, crystallographic compatibility between the film and the substrate. Do they have the same crystalline structure, like cubic on cubic, hexagonal on hexagonal, and so on? Generally, the grain size of the film increases with its thickness up to a certain thickness. The grain size increases with substrate temperature, and it can also increase with annealing temperature after the growth. Amorphous growth is favored at low substrate temperature. It is favored with the introduction of reactive impurities, and it is favored for low evaporant energy techniques such as the physical vapor deposition techniques, pulse laser deposition, E-beam, and thermal evaporation. Let's now talk about structural defects. Structural defects are incorporated into thin films either during growth or by post-deposition processing. These include grain boundaries, dislocation lines, stacking faults, and point defects. These defects may arise from misfits between different islands, substrate film lattice mismatch, and the presence of inherent large stresses in the film. Porosity is a property that is very related to the structural properties of the film. In general, porosity is not desirable in a film. However, certain applications, such as catalysis and sensing, require porous films. There are many types of porosity, like open porosity, in which pores are connected, closed porosity, in which pores are isolated from each other. In that case, they are called voids, and pinholes, in which pores extend through the deposit from the surface to the interface. Voids formed by the growth process, like columnar structure, or by agglomeration of defects during or after deposition. Porosity may affect film properties in a number of ways, since it will result in high chemical etch rate, high corrosion rate, easy contamination, reduced adhesion, and reduced refractive index. Another property which is very related to structural properties is the density of the film. Most deposition techniques create film densities that deviate strongly from the bulk density of the respective material. Lower density results from gas incorporation during the growth method, crystalline disorder and voids, presence of foreign materials, material that is not stoichiometric. The properties that are affected by the density include the optical properties, especially the refractive index, adhesion to the substrate, crystallization of the film, stress development in the film, and the chemical stability or instability of the film. Let's now move into the mechanical properties of the films. We talked about the structural properties. Now let's talk about the mechanical properties of the film. The mechanical properties of thin films are different from those of the bulk material because of the unique microstructure and density of thin films, the large surface to volume ratio, the reduced dimensions of the films, and the constraints caused by the substrate. The mechanical properties of interest for thin films include the stress, hardness, elastic modulus, and adhesion. So let's talk about each one of these. Start with the stress. Atomistically deposited films have residual stress, which may be tensile or compressive. The sources of stress include different coefficients of thermal expansion between the film and the substrate, atoms not being in their most energetically favorable positions, and phase changes in the film material after deposition. These residual stresses are very sensitive to substrate configuration and the deposition parameters. Lattice strain is caused by residual stress and represents stored energy. Film stress is an important factor in the adhesion and stability of the films. High compressive stress produces blistering of the film from the substrate, removing the film from the substrate. High tensile stress produces micro cracking of the film, and the cracks tend to meet orthogonally and form polygon islands. If the adhesion between the film and the substrate is high, the stress can cause fracture in the film or substrate material. The film buckling or cracking may be time dependent and depends on the moisture available in the ambient atmosphere. The second mechanical property is the elastic modulus. An accurate determination of the elastic properties of the coating is desirable for choosing the correct coating material and film thickness to prevent plastic deformation or cracking of brittle materials. The elastic modulus is defined as the stress versus strain for the material under elastic deformation. Thin films have been shown to have very high elastic moduli, up to 25% higher than the bulk, due to surface spinning of dislocations. Finally, let's talk about hardness and adhesion. Hardness is defined as the resistance to deformation. The hardness of a material may be influenced by the grain size, defect structure, microstructure, and density. For all practical applications of thin films, a certain degree of adhesion is required to guarantee the functionality of the coated part. The quality of adhesion mainly depends on the interface layer between the coating and the substrate. Adhesion is defined as the work that is necessary to separate atoms or molecules at the interface. Finally, the third type of properties, we talked about structural and mechanical. The third properties are the optical properties. Thin film materials are optically characterized by the complex index of refraction. Generally, the optical properties of thin films are somewhat different from those of the respective bulk material. The observed values of the refractive indices are usually lower, and the extension coefficients are higher than the optical constants of the same bulk material. Additionally, the resulting film properties are strongly influenced by the deposition method and the selected deposition conditions. When a beam of light is incident on the surface of a sample, part of it is reflected, part is absorbed in the film, and the remaining part is transmitted through the film. If the surface is rough, scattering takes place. So we have four processes: reflection, absorption, transmission, and scattering. All of these properties are functions of the index of refraction. Absorption in metals is caused by free carriers. Absorption in insulators is caused by the band gap. In both types of materials, there is additional absorption related to defects such as structural or chemical defects. Metals are characterized by high reflectance and therefore they are opaque. Insulators are characterized by their high visible transparency. Luminescence refers to the emission of light by the material. This can be induced by light, in which case it is called photoluminescence. It can also be induced by heat, thermoluminescence, by electrons, cathodoluminescence, or chemical reactions, in which case we call it chemoluminescence. In semiconductors, luminescence yields or can yield information on the band gap of the material. It can also originate from defects and impurities, and therefore it can yield very valuable information about these defects, their density, location in energy, and nature. Finally, we talk about the electrical properties of thin films. The solid-state revolution has created important new roles for thin film electrical conductors, semiconductors, and insulators. What was accomplished with large discrete electrical components is now more efficiently and reliably achieved with microscopic thin film-based integrated circuit chips. A current of density J is said to flow when a concentration of carriers with charge Q move with velocity V past a reference plane in response to an applied electric field. And these quantities are related by the famous equations that are related by Ohm's law, as we can see in here. Resistivity, which is the reciprocal of conductivity, is the quantity used to characterize the electrical properties of thin films. There are two approaches to study the conductivity: an empirical or experimental approach, which relates the conductivity to temperature, composition, defects, and electric field, and a fundamental theoretical approach, which relates the conductivity to the band structure of the material. Important factors that distinguish the electrical properties of thin films from the bulk properties include size effects, such as surface scattering, quantum mechanical tunneling, the method of preparation, the electrode effects, do they form ohmic or rectifying contacts, the degree of film continuity, the existence of high electric field conduction phenomena, and high chemical reactivity such as aging, water absorption, and oxidation. Let's now talk about metallic films, the electrical properties of metallic films. The total resistivity of a bulk metal is given by this equation, in which the total resistivity is the sum of the thermal resistivity due to temperature, the impurity resistivity due to the presence of impurities in the metal, and the defect resistivity due to the presence of defects in the material. Thin films have additional scattering from film surfaces and grain boundaries. Therefore, thin metallic films always have resistivities higher than that of the bulk. What about insulating films? These materials, the insulators, are characterized by the presence of an energy gap in their band structure. The band gap ranges from something like 0.6 eV in germanium all the way to 10 eV in silicon dioxide. An insulator is a material that possesses very few charge carriers. This is a consequence of the large energy gap of these materials. However, insulating films are generally amorphous. Thus, fuzzy tails arise both at the top of the valence band and the bottom of the conduction band. These tails extend into the gap and overlap to form a continuous electron state density. When this happens, insulators become semiconductor-like. Due to structural defects, there may be a relatively high density of charge carriers. They tend to be localized or trapped at these defects for long times, and the insulating behavior stems from such carriers having low mobility. The resistivity of semiconductors can be lowered and controlled by the addition of intentional impurities by a process called doping. When an insulator is sandwiched between a combination of metal and semiconductor electrodes and an electric field is applied, electrons, holes, and ions may migrate, giving rise to measurable currents. The conduction mechanisms in insulators include Schottky emission, tunneling, surface charge layer conduction, ionic conduction, and intrinsic conductivity. This is about the electrical properties, and of course there are other important properties we didn't talk about. They are specific to certain applications like thermal properties, chemical properties and composition, and magnetic properties, which are very important, for example, in the field of recording materials and superconducting materials. With that, we finished the fourth part of the presentation, which is about the properties of thin films. Now we move into the fifth part, in which we talk about the characterization techniques that are used to study or determine the properties of thin films. There are, of course, tens, maybe hundreds of techniques that are used to determine the properties of materials in general and thin films specifically. Here are some of them. Some of them are thickness techniques. Some of them are imaging techniques to look at the surface and see what kind of topography or morphology is there. There are techniques based on electron beams. You bombard the material with electrons, and what happens is you have secondary electron beams generated or X-rays generated. There are techniques dedicated to determine the structure. There are techniques based on X-rays. There are vibrational techniques that look at the vibrational properties of the material, nuclear-based techniques, mass spectroscopic techniques, and optical techniques based on ultraviolet visible spectrophotometry. And in addition to all of these, there are property-related characterization techniques to determine the mechanical, electrical, magnetic, and environmental properties. So you have many techniques. We will just look at some of them. So we will look at techniques to determine the thickness of the films, techniques to determine the structure of the film, techniques to determine the chemical composition of the films, and techniques to determine the optical properties of the films. These are again just examples of the many techniques we have seen in the list before. The most important and direct technique to determine the thickness. Thickness is a very important parameter for thin films. Many properties are dependent on the thickness, and the most direct technique to determine the thickness of the film is called surface profilometry, in which a very fine stylus, usually made of tip that has a radius ranging from 0.2 to 25 microns, scans across the surface at a very light stylus force. As the sample moves under the stylus and the stylus encounters various surface features, a vertical motion of the stylus is detected, and that will produce a vertical structure that shows the step height of the film, and from there the thickness is determined. Many techniques are used to determine the structure of thin films. The most important one is the X-ray diffraction, which is based on Bragg law. Here you bombard the sample with a beam of X-rays, and you observe the scattered X-rays using a device called a diffractometer, like the one shown in the middle in here. And when you scan over all the angles, typically from 0 to 80 degrees, you have a pattern like the one shown on the top right, and that's a typical XRD pattern, from which you can know the structural properties of the material, like is it amorphous, is it epitaxial, is it polycrystalline. You can also use these structures to determine the grain size or lattice size, to determine the degree of crystallinity, the presence of stress in the film, the lattice parameters, the structure itself, is it cubic, hexagonal, or rhombic, and so on. A wealth of information can be obtained from an XRD pattern. Scanning electron microscopy is a very powerful technique in which a beam of electrons is incident on the sample surface. It is used to scan through the surface, and as it does so, we detect the reflected electrons, and these can produce very powerful images on the micro scale or even sub-micron scale that shows us the topography and morphology of the film, and that will tell us a lot of information about the growth process, and it can also say a lot about the suitability of this coating to certain applications. A variant of this is the transmission electron microscopy. Here the electron beam is not reflected, but rather it passes through the film. So it has to be a very thin film for the electron beam to pass through, but once it does so, it is a very powerful technique that can tell us about the structure and crystallinity of the film. More recently, a new technique was developed called atomic force microscopy. It is like SEM, but instead of using an electron beam, a laser beam is used to raster the surface of the film, and that can produce information on the nanoscale about the topography and morphology of the film, and that can yield very important information about the growth mode of the film and the surface roughness of the film. In XRF, you detect the emitted X-rays by the samples. In XPS, you detect the emitted photoelectrons emitted by the sample when it is bombarded by the X-rays. This is a very powerful technique. It can tell us the composition of the film, and most importantly, it can tell us the oxidation state of the elements making up the film, which can be extremely important in many processes like catalysis, corrosion, and sensing. It is a surface technique, it's not a bulk technique, so it can detect only the few top monolayers of the film. RBS, which stands for Rutherford Backscattering Spectrometry, is another powerful technique to study the chemical properties of the films. It has many advantages. First, it is a bulk technique. Okay, it's not surface like XPS. It can penetrate the whole film. So in that case, it is like XRF, but it has an added advantage to XRF, and that is it tells us how the elements are distributed spatially along the thickness of the film. A third advantage of RBS is that it can detect the presence of hydrogen in the films. The disadvantage is, as you can see in this picture, it requires huge equipment. It requires a tandem accelerator like the one you see in here. So it is really a very sophisticated technique, and it needs a lot of space and preparation to yield the desired spectrum. Now let's look at some optical characterization techniques. The most widely used one is called spectrophotometry, in which you bombard the sample with a beam of light, and you either detect the reflectance, the transmittance, or the absorption of light through the film, and that's called spectrophotometry. It can tell you a lot of information about the material, like for example its band gap and its optical constant. Another widely used optical technique is spectroscopic ellipsometry. In here, you bombard the sample surface with a polarized beam of light. It will reflect from the sample with a different state of polarization. So, by studying the state of polarization of the reflected beam and comparing it with the incident beam, you can, from that comparison, determine the optical constants of the film, like the refractive index, the absorption coefficient, and the extinction coefficient. A third optical technique is photoluminescence. We already talked about it before. Here is a typical instrument. You shine a laser, for example, on the sample. If the sample is optically active, it will emit light. You detect the emitted light, that's the luminescent light, you detect it, and from there you can get a lot of information about the band gap, the defect states, their locations, and even the chemical composition of the sample. So these are some of the main or most important characterization techniques used to study the properties of thin films. That finally brings us to the last part of this presentation, which is about the applications of thin films. Thin films are important in their own regard from a fundamental theoretical point of view, because they can tell us a lot about the properties of materials, and that's why we started the talk with materials research. So they are at the heart of materials research. But in addition to that, they have found plenty of extremely important applications in modern technology. Let's look at some of these applications. We start with the most important one, which is the usage of thin films as protective coatings. Thin films are used to protect against corrosion, protect, for example, machines and pipes against corrosion. They are used in wear reduction to coat cutting elements or tools and protect them against wear. They are used to protect against oxidation, and most importantly, they are used as thermal barrier coatings. The second class of applications of thin films is their application in energy-related fields, like their applications in photovoltaics and solar cells. These are heavily based on thin films, either as the active layers that interact with light to produce the electrons, or as transparent electrodes, or as metallic electrodes to carry the current into the external parts of the circuit. Energy-efficient coatings present another example of the usage of thin films in energy applications. They are used to save or conserve energy in commercial buildings and automobiles. We can also have another class of these, which is called smart windows, that detect the change of the environment and accordingly change their properties and save the energy accordingly. Thin films are used in the production of fuel cells for the production of energy. They are used in solid state batteries, and they can also be used in catalysis and polymers. Optical applications of thin films have been the most traditional ones. They have been used initially for optical applications, and then came the other applications. So optically, thin films can be used to make mirror coatings, anti-reflection coatings to reduce the reflection of light and therefore allow as much light as possible to fall on the material. This is very important, for example, for solar cells. They can be used to fabricate interference films, which are used to pick or select a certain band of wavelengths and allow them to pass and reject the others. They are very important for laser coatings, laser cavities, semiconductor lasers, gas lasers, and they are of course used in ophthalmic coatings to make the glasses that we wear. Optoelectronic applications of thin films include the production of light-emitting diodes, and we know now how important are these. And inherent in the production of LEDs, you definitely have thin film growth at one or more steps of the production of LEDs. Likewise, they are heavily used in the production of laser diodes, which are heavily based on thin films. They are also used for the production of optical recording and data storage materials, and they are used in integrated optics, for example, in the form of waveguides. Semiconductor applications of thin films have become extremely important. They are an integral part in the semiconductor devices that are used in microelectronics. They are also used in sensors and actuators, for example, in MEMS, micro electromechanical sensors. Gas sensors are basically thin film in nature. Magnetic sensors, piezoelectric sensors are all coating based. Super lattices are based on thin films, as well as quantum wells. So these are some of the very important recent and traditional applications of thin films. With that, we come to the conclusion of our seminar. I hope I have elucidated the importance of this extremely important field of science and application, thin films and coatings, which, as we said at the beginning, stands at the cross-section of many fields of science and engineering. Finally, I leave you with some of the resources that I have used to prepare this seminar.